Good evening, everyone. Well, we started our discussion on ANOVA 2 days ago, and I said, not ANOVA, we have talked about ANOVA. I think it was regression. Regression. We talked about ANOVA previously, and I said that both of them are the same. They are two faces of the same coin. It's just a different way of looking at the same thing. And I said that in those days, the researchers that were involved in experimental design, they use ANOVA a lot because they tend to have many groups, more than 2 groups, 3, 4, 5, as many as possible they can have. So in those group are actually small group because they tend to control for confounders right from the design stage. And that's why for each of these factors that is different, they have different group. So they use ANOVA. Why the observational researchers, they are not doing experimental design? Because by the nature of that, their own design, because they cannot perform experiment in all situations because of ethical issues. They cannot perform an experiment on human being. So even animal self, to perform experiment on animal, it's a big issue. So most of the time, the only experiment we can perform are something that are not so like health education or this maybe you give vaccine to some people, and it has to be maybe a new vaccine. If it's well established, you cannot withhold the vaccine from other people and say you are doing stuff. No. So maybe if it's a new vaccine that is coming, okay, try to give to some. If you happen to work later, you want to compare with previous one. If you work, you have to give to even those people that you didn't give to before. So experimental design is very tricky and a lot of ethical issues. So in situation where you cannot do experimental research, you still have to do research. So the observational researcher, when you didn't do experiment, that's observational. So they cannot control for the confounders from the outset, like the experimental researcher do. What they do is to wait for the analysis time to run the analysis and control confounder. And that's why they use regression to control for confounder during analysis. While the experimental researcher use ANOVA, but whether both of them are the same, and that's what we want to look at. So it was later intelligent people get to know that both ANOVA and regression, they are two faces of the same coin. So that you'll be able to conceptualize it, is the data we have worked on before, or that I presented in the last 2 lectures, that I tried to bring something to explain so that maybe you can conceptualize, you can understand the logic behind the two of them, how two of them are actually the same thing. No, so let's still come back to that libido score for 3 groups of participants with different interventions. We remember, we say that there are 3 groups, 5 people in each group. So to know the effect of Viagra on libido. So of course, you divide them into 3. The first group was given nothing but placebo. That is, what you give does not have active ingredient. So it's more like control group. The group 2 was given low dose, and group 3 given high dose. So after their performance, you administer the scale for them to talk about how the libido was scored on the scale of 1 to 10, and they give their score. Well, I wouldn't know if it's 1 to 10, because I have someone scored 7 here. Maybe around 10. It's called the libido. So you can see the score of 5 each of the 5 people in each, and we have the mean the mean by X for each of them. Group 1, the mean average value is 2.2. Group 2, which is low dose, 3.2. Group 3, which is high dose, the mean is 5. You can see their standard deviation, 1.3, 1.3, and 1.58. You can see their variance. Variance is just square of standard deviation because standard deviation is square root of variance. Though logically, the one you calculate first is variance. For its variance, you first calculate from the data because after you calculate the mean, calculate the variance. You cannot calculate the standard deviation without calculating the variance. But because the standard deviation, why we quote it more? Because it has the same unit as the mean, as the original data. The original value, the unit is the same thing as the mean, and that of standard deviation. Variance, the unit is square of the original unit. And you remember the reason is because we square along the way. And in order to bring it back, so after you have calculated the variance, to bring the unit back from the square, you now calculate the square root so that the unit will come back, and that is where you now get standard deviation from that variance. So both of them are interchangeable. If you square standard deviation, it gives you variance. If you find square root of variance, it gives you standard deviation. So we talk about the grand mean also. That is, if you forget about group and you just add all the 15 scores together, you can calculate the mean, which is the grand mean. And you can calculate the standard deviation, which is grand standard deviation, and calculate the variance, grand variance. The another way of getting the grand mean, apart from adding all the 50 together, you can actually add the 3 means together and divide by 3. So I will not explain some of these things, how we generated all these things we have explained before there. Where I want us just to know is that the language what we call sum of square, and it is really understood with the ANOVA how we get what we call sum of square. I say there are 3. Maybe I will come back here. Let me show you the next slide. We look at the similarity between them, but that similarity is in the context of the level of variability. There are levels of variance of variability, 3 levels in a data set where you use ANOVA or regression. There are 3 levels of variability. So, well, when you have groups, in case of ANOVA, you have more than 2 groups, 3, 4, 5, whatever. There are 3 levels of variance. And the same thing, the way it appears in ANOVA is the same thing in regression. So now you remember I demonstrated in that previous slide about the 3 levels of variability. If we use the ANOVA, because to me it's easier to conceptualize with ANOVA. Okay, the first one is within each group. Within each group, you know how do you calculate variance? You calculate mean. You now remove mean from each value and now square it and now sum it together and divide by n minus 1, which is the degree of freedom. That's how to calculate variance. Square root of variance is the standard deviation. So both standard deviation and variance, they are the measure of variability. So we talk more of variance. So it's actually the same as I told you before. Standard deviation and variance are like water and ice block. If you want water, if you want ice block, you freeze water. If you want your water by you melt the ice block. Same thing with variance, just a square root or square. Now, for you to calculate variance, you already know you have to know the mean first. Mean is the bar x. You remove it from the original value, which is the x. We know that when you do that, the difference, because mean is usually close to the middle. So if you remove mean from some value that are less than the mean, it give you negative. The one that are equal to the mean, it give you 0. If you remove the one that are greater than the mean, it will give you positive because you are removing mean from the original value. So it's associated, since the mean is in the middle, the value, if you sum all the negative together and sum all the positive together, it gives you 0. That's why The intelligent people all over that's why they skill. They don't do anything about that X1 or S bar. Before you can do anything reasonable, because it adds up to 0, you square it first. It's the square that removes negativity. You know, -3 times -3 is 3, is 9. That is, when you minus times minus, it gives you positive. So now, for the first level of variance, is the variance within each of the group. Each of the group means that you remove the mean of each of the group from the value and you square it. When you square it, because we now add it together, is the sum of square deviation from the mean. The sum of square deviation from the mean. Sum of square deviation from the mean. So, but people just make it short, sum of square. Sum of square. That's what you see when you are running ANOVA and you are running regression. It is simple when you are calculating variance, even from normal calculate variance standard deviation. By x minus by x, you remove mu from x. You square it and you sum it together. That is sum of square. But if you want to now know the average sum of square, the average square deviation, when you have sum it together, you calculate the average, but you don't calculate the average by dividing by the sample size. You will divide by the sample size minus 1, which is the degree of freedom. I've explained the reason before. So, but the issue is see the average deviation, square deviation from the mean. And that is the variance. That average square deviation from the mean is the variance. But this sum of square is very, very important before you divide, calculate that variance. That sum of square is very, very important for you to conceptualize. So, when that one, that is the fourth column here now. That is the fifth column rather. When you add it together, it's 23.6. So what that one does tell you is the variability, the sum of square within each of the group. You know the way they did it, forget that they are arranging 1 to 15. 1 to 5 is first group. 6 to 10 is second group. 11 to 15 is the third group. As you can see in the second column, is denoted there. So when you are removing, what they actually remove is the mean of each group from the value for each group. So it's just align. So when you get all these things, that's sum square everything and sum it together, give you 23.6. That's the sum of square within. And this sum of square within, remember, I saw when I talk about this regression, you know, I show you that this is this regression plot. I told you also that the first plot is the mean of y. Because in regression now, you know, you are talking of the outcome variable, which is the y. The mean of y. If you calculate the mean of y, if you look at the level, the dot for each data set, you can see that it's averagely far from mean. Mean is the horizontal line. But the regression line you have drawn is this slanting one, the second one. You will see those points, they are closer. The lines are, the regression line are closer to those points than the mean line for that first graph. So we have already said that that mean is crude. But this one, the difference between the regression line and each point, that is the residual. So if we sum these residual, some are above, some are below. Those ones are above, they are positive. The one below, they lie negative. So if you sum it, if you square it, that's a sum of squares, and sum it together, that is sum of square residual. This sum of square residual is the one that corresponds to sum of square within in ANOVA. Can you see? Look at this table. Variability within group. Sum of square within for ANOVA within groups is the same thing as sum of square residual in regression. Now, if you look at the second one, which is this one now, from that is column 6 and 7, fourth to and third to the last column I'm talking about. If you look at it, bar x minus double bar x. Bar x means the mean of each group. Double bar s is the grand mean. That is, if you forget about group and add everything together and calculate the average, that will be the grand mean. So that is the one that is looking at how different are the different groups. That's what that is comparing how different the different groups. So that is whatever variable. If you by the time you square the sum of square it and sum it together, it gives you 20.1335, which is the sum of square between groups. And this sum of square between groups is the one that corresponds with this last one here, the last graph, which I told you that. I already said the mean is a cruded one. It's a cruded model. It cannot, that the prediction of the mean is not as good as that of the regression line. But how good we want to compare the regression line? How do we know how good it is? We can still know how good it is by comparing it with the crude, which is the mean. When you now overlap the two graphs, is the difference. The difference, so that sum of square residual is what the regression line cannot explain. It is what it can, that's its residual. It cannot explain about the variability of the data set. And the total to be explained is what the mean is showing, first graph. So if you now remove what it cannot explain from total to be explained, it gives you what the model has explained. Well, that's why they call it sum of square model. Because that's the one that actually shows the model. And the model is the one that corresponds with between group in ANOVA. So sum of square between group, same thing as the sum of square model in regression. The total sum of square for both of them is the same thing. If you look at it now, for ANOVA, ANOVA will say the total sum of square, where you get it here, look at the last two columns. You remove the grand mean from each value, irrespective of which one. Collapse all the 15, remove the grand mean from each value. Square it. So when you sum it, it's the total sum of square. If you had the sum of square within plus sum of square between, it adds up to total sum of square. Look at it. 23.6 plus 20.1335. It gives you 43.7335. You see, very straightforward. You will see that the sum of square within and plus sum of square between make up the total sum of square. So in the regression graph, the total sum of square is the one that provided by the mean. But the mean now is like the grand mean now in ANOVA. So the variability, that's the total variability to be explained. So now you will see total, both of them, they correspond. But the within in ANOVA correspond with between in residual in regression, while between ANOVA correspond with model in regression. Now, the model is the one that's okay. This model you have built, the variability you want to detect is the model. Is the model. So in ANOVA, if you look at it, in ANOVA, how do you know, okay, if this model is good? What we do is, okay, the variability explained by the model, which is sum of square between in ANOVA. How big is it? It is when it's far, far bigger than the one the model cannot explain. The one within is the one they cannot explain. What they can explain, if it's far, far bigger than what they cannot, you can say it's good. So if you want to now, this is sum of square, but if you want to actually calculate the variance, you just divide each of them by the degree of freedom. Look at 23.6 divided by 12, because that's the sum of square within. And the degree of freedom is 12 because there are 3 groups. Each of them are 555 sample size, 555. So the degree of freedom for each of them will be 5 minus 1. So 5 minus 1 is 4 in 3 places. So you divide that 23.6 by 12. It gives you 1.967. That is the mean square within. That is mean square, that's the meaning of variance. Mean square within, the variance within. And the variance within, you want it to be so small. That's what the model cannot explain. That's the within the data group. But the one that is between the different groups, which is what we are testing, is the sum of square between, which is 20.1335 over 2. You know, there are 3 groups. So 3 minus 1, that is 2. So the degree of freedom here is 2. So you divide it by 2, it gives you 10.067. So the variability in the model can explain is 10. The one you cannot explain 1.96. So it's far. So if we move at the other one, that is the F ratio, the ANOVA statistic, which is mean square between mean square with. Give you 5. So it's greater than 1, because if it's more than within, it's greater than 1. Not only greater than 1, it's so great, 5.119. So it's significant. If you go and check the statistics, but of course the computer give it to you if it's significant. So in the ANOVA, it's the same thing. In the regression, rather, it's the same thing. In regression, it's just okay. The F ratio is sum of square model over the sum of square residual. So that is where, to explain every other thing now, let's go to the output. No, we don't have a luxury of source with hand. Let's look at the ANOVA output with SPSS and that of regression for the same data set. Look at for the ANOVA output, you can see placebo, the sample size is 5, each of them 5, 5, 5, total is 15. The mean for each group, which we already know, the standard deviation, then come to, well, leave all these for. Then let's come to the next table, ANOVA. You see, between groups, the sum of square 20.133. That's what we have demonstrated. Within groups, 23.600. The total will be addition of the 2, which is 43.733, which you saw. Can you see? By solving with hand, that was you saw about solving with hand. The same thing. So the SPSS brought it out. Exactly the same thing. So the degree of freedom, you remember, for within group is 2, and between group is 2, within group is 12, and the total is 14. If you had 12 and 2, I give you 14. And can we imagine if we even want to the degree of, if you add everything together is 15 minus 1 is 14 also. I see total degree of freedom is 14. Then within group is 12. And is 12. Between group is 2. 12 plus 2 give you 14. So the mean square is you divide by each of these sum of square by the standard degree of freedom. 20.113 divided by 2 give you 10.067. 23.60 divided by 12 it give you 1.967. So F ratio is the 10.067 over 1.967. That is the mean square between over mean square within, and it's statistically significant. Now, if you run the same thing, this is regression. And in order to run this regression, what we do is that we give, we have already coded this placebo 1, this one 2, this I 3. We have to create a dummy. Because there are 2 groups, we created 2 dummies. If I show you the way it is in next lesson, we created 2 dummies. The 2 dummies, if there are 4 groups, we created 3 dummies. That is, you have to hold one group constant. For example, now we may hold a placebo, which is the smaller, the lowest one, in our constant. So we compare placebo and low dose. That's one dummy. What we just actually do in dummy, there's no big deal there. The SPSS, the dummy, the first dummy we want to create between placebo and low dose, anyone that is low dose, that is placebo, low dose there, we mark it 1. Anything that is not low dose is 0. Both placebo and high dose, 0. So when it comes to the second one, for high dose, anyone that is high dose, we mark it 1 for that dummy. The rest is 0. So can you see now? It is only low dose and high dose that has dummy now. So the first one, when the high dose, low dose, 1. Any other thing is 0. The second dummy, high dose, anywhere there's high dose, put 1. Any other thing is 0. So that shows that there's no dummy for the placebo, because that is the reference. They're using as reference. So that is why when we are running it, so it's not the same. It's not the same because in this ANOVA now, when we want to run, okay, libido, then we have group dose. But here is the yes, libido is the outcome for regression. But it's those two dummy going to use to run. So the first table, variable entire. You see high dose versus placebo, low dose versus placebo. Can you see? Those are the two dummy. And the variable is libido. So if you look at leave model summary, let's come to ANOVA table. The ANOVA table, can you see? Maybe what I should have done, I will have put this one beside the other one so that you will see the way. Let me see this come. So that you can, okay, I want to, okay, let me stop sharing. I will share it now, because I want to, so that I can even put this one beside. Just 1 minute. That ANOVA table in the regression beside the ANOVA table in ANOVA itself. So let me reshare. So this is what I've done. Look at this. ANOVA itself in the ANOVA. That's the table in the middle. The one in the regression, can you see? Can you see the same thing? So can you see the other model you now see between group is the same thing as a regression. That model is the word, and what do I call it? Expression called regression. Within group is the residual. Can you see? Can you see? Within group, residual. Total is the same. Can you see the value? Look at the value. 20.133 for each of them for between group, for sum of square, for residual within group, 23.600 for the total. Can you see? Can you see the degree of freedom? 212.14. Can you see the mean square? Can you see the health? Can you see the significance? Can you see? So this middle one is just ANOVA pure. But this one is ANOVA run in regression. See exactly the same thing for the same data set. So all these, so that if you now look at back to the regression, the last table here, which is coefficient. This coefficient, what it tells you, can you see? You see, in our regression, you remember our regression equation, we have y is equal to constant, which is b0, beta 0, and the other one will be bx. That constant is the value of y when s is equal to 0. You remember that you use the libido, the placebo, as the reference. So the mean of the placebo is the constant there, 2.2. Now, you know the low dose versus placebo is first dummy. You are comparing low dose and placebo. So the mean for the low dose is 3.2. So the one for placebo, which is the constant 2.2, when you remove it from 3.2, it give you 1. That is that one you are seeing, the difference between them. So the second dummy, which is high dose versus placebo. The mean for the placebo is 2.2. For the high dose is 5. The difference between 5 and 2.2 is 2.8. Can you see? So that is the way it works. And the other thing, this second table here, model summary, up on the right side, is 0.679 is what we call that is the R. If that is actually the R, which is the correlation between the exposure and between the two variables involved. Now, R square is the square of R. 0.679 times 0.679 give you 0.46. And this one, you express it as percentage, 46%. That is a variability, variation in the libido that is due to this Viagra. So it's not only Viagra that if you don't even even look at the person they give placebo, still have not that the libido will be 0. So if you don't use Selena, it doesn't mean that the libido will be 0. But it's trying to say what proportion change, percentage change in the libido, variation in libido, that is accounted for by that variable change in the dose of Viagra you do is 46%. So the last thing I just want to explain is look at, I think I showed you this one in the last lecture when I was talking about ANOVA also. So what it just showed in the regression, what it just showed now. Can you see these are the means of each of the group. The green is first group. These are their different values. And the mean for first group 2.2. Can you see that line that that attached to that green dot? Can you see 2.2? Libido is vertical. The participant is horizontal. Can you see? That line is around 2.2. And these are the different values. So what is showing you the relationship between the mean and each value. 2 have value above the mean, 3 have value below the mean. And it shows you the distance between them. The same thing you have for the low dose, which is showing a triangle. Low dose group. Can you see the mean is 3.2? You can see 2 have value above, 3 have value below. Also, the last one, which is the high dose, the mean is 5. Can you see? And 2 have value above, 1 have value that is equal to the mean, and 1 2 have value below. So you will see that the difference, the two determine the created, the one between placebo and low dose, and the one between placebo and high dose. So you see between their means, we know we have already removed for the B1 is the difference between the mean of first group and second group. And we know that it's 5 the other time. 5. If you say 3.2 minus 2.2, will give you 1, not 5, 1. So the other one, the B2, is the difference between the mean of the first group and third group, placebo and high dose. You remember for high dose, the mean is 5, placebo is 2.2, the difference there will be 2.8. So can you see those regression value, the coefficient B1 and B2? That's what it's showing. I'm trying to show you that representing running it with regression, what the way it shows, graphically, just for you to conceptualize it. So this thing you cannot totally understand unless you have hand-on how to do it. You'll be able to see the way it is. Don't know if there's any question. Even the turnout for the something is very low. So let's 6 of you. 3 started. We join. Any question? Any question? I've been here from the beginning. You understood it. People that
Excuse me,
join
sir.
later. Yes, go on.
Sir, what I want to ask is this placebo, low dose, and high dose of Viagra.
Mm-hmm.
The duration of exposure sort of is limited. So why should we have a summary over such a short duration? Because if they have those exposures for a longer duration of 2 weeks, 2 months, 3 months, for example, how do we know if that low dose and high dose are still effective versus placebo? I don't know whether I make my sense.
Okay, now when in statistics, the time duration does not come in the sense that the relationship you are looking at is between the dose and the performance. If you want to bring in another factor, how long did they use it? Are they using it? That's another thing, right? And the way they did this one is that they give out after the performance with this. Well, if you want to use when you use it today, you know the performance today. As you take the something, is it not when you are about to perform that you take the dog and you perform? Let's see the effect. If you want to have accumulative something, if that factor were to come in, that would be a different thing. Okay, you want to say people that use it for so long, how do they, maybe what we are measuring is average performance over time. Because you can, if you do it, let's say you do it for 1 month as you see, and the person is taking the same dose constantly and is recording the performance. At the end of the day, you may decide to say what is the average performance. You may now want to see, okay, maybe some people take it for longer time, lower time. How does it, that factor is not here now. We are talking of two variables involved. So that one is a possibility, but it's not involved here now. I don't know if I've answered your question.
Yes, I think so.
You
Yes, sir.
think you are not sure, you just think.
No, I can. Everything comes up as a variable to be measured.
Exactly. It depends on what you want to
So
measure.
yes, sir.
Even when you do a study now, you can calculate, you can collect a lot of data. But when you are doing your statistics, precept by precept, you are trying to look at the relationship between this and this, this and this. You may not bring all of them together. It depends. So it depends on what you are calculating per time.
Yes, I get the idea. Yes, sir.
Yeah.
Thank you, sir.
Okay. Any other one? Dr. Lanino, you came late.
So sorry, sir. Good evening, sir.
Good evening. Any question?
I was initially in a to, I think so. No, sir.
Is understood or is confused? You don't know which one.